Hello, I hope everyone is doing well. Today we're going to cover one last topic in Chapter 16, and then we'll be done with Chapter 16 content. So today we're going to cover Lewis acid-base theory. So this is one last definition of acids and bases. This one I don't use that often. I tend to refer more to Bronsted-Lowry acids and bases. But Lewis theory is important because there are some cases where acids and bases aren't transferring protons. They're actually transferring electrons. So Lewis acid-base theory focuses on transferring an electron pair instead of a hydrogen ion. So a Lewis acid is going to be a lone pair acceptor. So it accepts electrons. And then a Lewis base is a lone pair donor. So it's going to donate a pair of electrons. So again, this theory does not require hydrogen ions in order to define an acid-base reaction. Now this does come in handy, especially for acids, because some acids don't have protons, but they can still act as acids. And in fact, we did see an example of that. We saw that aluminum 3+ can be an acid because it is a small, highly charged metal. But in general, our Lewis acid-base reaction might look something like this, where we have an acid with maybe a positive charge, and then a base with a lone pair of electrons, and then they're going to team up and form a molecule. So let's start with Lewis acids. Lewis acids will be electron deficient. So either from being attached to electronegative atoms, which are pulling electron density away, or from not having an octet. So Lewis acids must have an empty orbital willing to accept the electron pair from the base. So let's go over some examples of Lewis acids. So one example is boron trichloride. So boron, you might remember, is completely happy with just 6 electrons. It doesn't need an octet to be stable. So in this molecule, we have an incomplete octet on boron. But what's great about that is boron can take on 2 more electrons. So even though boron's happy with 6, it can have 8 electrons. So it would be a Lewis acid in this situation. Another example is the hydrogen ion. Now, even though Lewis theory doesn't require a transfer of a hydrogen ion, it can still occur. And hydrogen ions have an empty 1s orbital because it lost its electron. So that hydrogen ion can also accept electrons. And then I mentioned that aluminum 3+, that can also act as an acid. It's small and highly charged. Oh, highly charged. So it can also accept electrons. And then the last example of a Lewis acid is a molecule where the electrons can rearrange in order to create an empty orbital. So one example would be carbon dioxide. And let's say that this is interacting with water. So water in this case is the base, and carbon dioxide is the acid. So a lone pair from the oxygen and water can actually interact with carbon, and then one of the pairs of electrons between carbon and oxygen is going to move over and therefore create an empty orbital on carbon. So then carbon can actually accept the electrons from oxygen. So we'll end up with carbon bonded to 3 oxygens. So the oxygen to the right of carbon is going to end up with a negative charge because it's gained electrons. And then the oxygen below carbon will end up with a positive charge because it's bonded to 3 different atoms. So kind of similar to the hydronium ion. Now what's really interesting is the negatively charged oxygen is going to be attracted to the hydrogen down below, and it can actually grab onto that hydrogen. And then the electrons between hydrogen and the positively charged oxygen will be left on oxygen. And part of the reason that this occurs is oxygen would prefer to have a formal charge of 0. So if it can react with something to become more stable, it will. So now we'll end up with a carbon that's double bonded to 1 oxygen. And then it has single bonds with 2 OH groups. Okay, so again, the reason that carbon dioxide was an acid in this example is because it could rearrange its electrons and therefore open up an empty orbital. And that empty orbital can accept electrons. Okay. Now, Lewis bases are a little bit easier. The definition here hasn't really changed from our previous definitions. So in this definition, Lewis bases have electrons that they're willing to give away or share. So Lewis bases must have a lone pair of electrons that it can donate. So this is pretty similar to the Bronsted-Lowry definition. Now, anions are going to be better Lewis bases than neutral atoms or molecules. So if we have a neutral nitrogen with a lone pair, that's going to be less basic than a nitrogen with a lone pair and a negative charge. So for instance, let's look at some actual molecules. Ammonia, we know, has a lone pair on the nitrogen, and that nitrogen is bonded to 3 hydrogens. And that's going to be less basic than a nitrogen that's only bonded to 2 hydrogens, and it has a negative charge. So really anything with a negative charge is going to be a better Lewis base than something that's neutral. Now, generally, the more electronegative an atom, the less willing it is to be a Lewis base. So if we compare oxygen and sulfur, oxygen is more electronegative, so it's going to be less basic than something with sulfur in it. Now, the reason that's true is if oxygen wants to hold on to electrons, it's less willing to donate those electrons. Now, it can still act as a Lewis base, but it just won't be as strong as, for instance, something with sulfur in it. So let's look at an example of an acid, a Lewis acid base reaction. So the first example up above, we have boron trifluoride and ammonia. So boron trifluoride, remember boron has an incomplete octet when it's bonded to 3 atoms. So it can interact with ammonia because it has an empty orbital. So the lone pair on the nitrogen in our Lewis base is going to donate itself to boron. And then we have a molecule where boron is now covalently bonded to nitrogen. And we're going to call this an adduct. And then our second example involves the aluminum ion, which we said was a small, highly charged metal. So it can act as an acid. And we've actually seen this example before. So previously we saw that this small aluminum ion can form a hydrate by bonding to 6 water molecules. So those water molecules are going to act as the Lewis base because they have lone pairs. So in our first example, again, the base, which was ammonia, donates a pair of electrons to the acid, which was boron trifluoride. And that's going to generally result in the formation of a covalent bond. And I mentioned on the previous slide that the product that forms is called an adduct. So Arrhenius and Bronsted-Lowry acid-base reactions also fall under the category of Lewis reactions, but remember that Bronsted-Lowry acids and bases don't necessarily fall under the Arrhenius definition because the Bronsted-Lowry definition is a little bit more expansive. And then that's the same for Lewis acids and bases. They might not always fall under the category of Arrhenius or Bronsted-Lowry acids and bases, but that's because the Lewis definition is broader. So Arrhenius acids and bases are also Bronsted-Lowry and Lewis acids and bases. And then Bronsted-Lowry acids and bases are always Lewis acids and bases. So I guess we could make a little flow chart. So Arrhenius acids and bases do fall under the Bronsted-Lowry definition. And then both of those Bronsted, and then both of those definitions fall under the Lewis definition. But if we were to go backwards, not every Lewis acid is going to be a Bronsted-Lowry acid, and not every Bronsted-Lowry acid is going to be an Arrhenius acid. So we're kind of building and building and building up, and then we're expanding our definition each time. Okay. So that's actually the end of chapter 16. So again, remember to work on your chapter 16 homework on sapling. It never hurts to get a head start on that. And also make sure that you understand or work through the worksheet problems. And then also the study guide for chapter 16 is posted on the Canvas website. So make sure to work through that. And if you have any questions, always feel free to email me or set up a time for an office hour. All right, have a good rest of your week.